We're going to use Ampere's law to find the magnetic field generated by a current carrying wire. So let's begin by setting up some axes. So let me think about a plane transverse to my infinitely long piece of wire. I'm going to have a z direction along the wire, and then in the plane I'm going to have polar coordinates r and theta. So if we're going to use Ampere's law, we have to begin by making a symmetry argument about the form of the magnetic field. And what I'm going to claim is that the magnetic field will be in loops centred on the wire with the direction given by the right-hand rule. Now, there's nothing that's going to distinguish where I am in Z or where I am in theta. So B will be given simply by a function of r, the distance in the transverse plane that you are from the wire, and it'll be in the theta hat direction. Now we can write down Ampere's law. It says the integral around a closed loop B dot dl is equal to mu naught times the current enclosed by that loop. So we have to choose an Amperian loop, and the symmetry arguments we've just made suggest that what we should do is to choose a loop of radius r away from the wire. The magnetic field will be constant all around the surface, and any individual piece of that loop, delta L, will be in the theta hat direction at any point around. So it will be pointing in the same direction as the magnetic field. So now I calculate this integral, so I will get B at R, because that will be the same for all points around, and then I have to sum over all of these delta L segments round the loop. And that will be equal to the current enclosed times mu naught. And the current enclosed is just I, the current in the loop. Of course, here the summation over all these delta L bits going around the loop will just give me the circumference of the loop, which is 2 pi r. And so I get that the magnetic field is given by mu naught I over 2 pi r theta.